So you guys are, I mean, probably needs no introduction because we are, the audience is full of experts in the field, but still just to just as a preface, salt bridge, as we all know, ionic bonds, they are one of the major electrostatic component in both globular and disordered proteins, and they are formed when two oppositely charged side chains comes close in the three-dimensional context of a protein structure, and traditionally this has been identified as a threshold of 4 angstrom between a positive and a negative charge center coming from the two side chains, and as you can see, the repertoire of ionic residues or charged residues in proteins, and considering a near neutral or physiological pH, most of the residues are actually very much elongated, and they have a large number of rotameric variations. If you explore the Dunbach's rotamer library, you'll get 64 rotamers for arginine, 57 for lysine. So essentially they are very elongated residues. So that's one of the reasons for which probably there hasn't been a single report of a successful salt bridge design in designed proteins, because of if you are intending to design a salt bridge, a specific one, a standalone salt bridge, you are basically jamming a conformation of a joint double of side chains, a joint order pair of side chains, and given that they have large conformational variation, the feasibility or the plausibility is quite thin. For example, if you are trying to design an arginine glutamate salt bridge, so obviously it will eventually be jammed into one conformation, and that has to be sampled from a conformational space of 64 into 36. So you have very low probability of design rescue. We in our first study addressed this problem a little bit, and we came up with a hypothesis that probably could aid salt bridge design in the future. But still it is in a hypothesis, at a hypothesis stage, and I'll briefly talk about that as well. But before that, let us go back into the 90s. 1993, the first methodology was proposed to compute shape complementarity at protein-protein interface, and after 4 years, effectively the same group, they came up with the formalism to compute electrostatic complementarity at the protein-protein interface. This is very important for our context because this paper clearly showed that salt bridges can be stabilizing as well as destabilizing depending on the context. So that very salient feature imparts on salt bridges the capability to to trigger transitions, probably from order to disorder transition, or maybe transitions between multiple disordered states, the so-called phase transitions. And as we go along, probably this will be made more clear. But this paper was instrumental in structural bioinformatics of proteins, also in a way that they ruled out the complementarity for surface charge or any kind of charge distribution, and it was revealed that the complementarity at protein-protein interfaces in terms of electrostatics at least is in the anti-correlation of surface electrostatic potential, and those potentials contributed by all atoms, because Coulomb's interactions are essentially long-range interactions, they can be devoid of salt bridges as well. So in other words, they put some dummy atoms to effectively neutralize the salt bridges. So the salt bridges really didn't contribute to the electrostatic potential in one of their calculations, and those interfaces could still retain sufficient amount of electrostatic complementarity. So it's not only the salt bridges, but also rather a distribution, a particular set of distribution of partial charges throughout the protein that is actually giving rise to the complementary behavior. Now our focus here is on salt bridges. So in my first work, and this is basically my first paper this was the first paper as my as a corresponding author. We first tried to figure out the ionic bond networks within proteins, and this was a continuation of a numeric scheme which was previously applied to decipher the protein interior in terms of packing motifs. So we have all heard about secondary structural motifs. They are trivial in protein structures, like helix turn helix, and these the earlier work before that on packing motifs that revealed another set of motifs within protein in terms of packing topologies. And using the same numerical scheme, here we identified ionic bond networks within proteins, and we did it for globular, disordered as well as PPI complexes. I'll briefly describe the numeric scheme. So basically you compute the degrees of each of the nodes in a network, and then obviously first of all, these networks are ionic bond networks. So basically this is a negative charge center, then this is a positive one, then again you have a negative one, like that. So they, the salt bridges are not standalone. They can be extended as well, and how different topologies can be sampled, how different branching and different direction of connections between the adjacent ionic residues. That was the thing that we are looking for. So here you compute the degrees of each node, and then you figure out the nearest neighbors and compute their degrees, collect them as elements of an array, and sort them in descending order, and then concatenate that number string with the degree of the original node. So by that you assign each of these nodes a topological identity, for example, and then further join those number strings by a delimiter after again sorting it in descending order. So that's basically the numeric scheme. An example would clear it for you. Let's take this one. So 211 refers to this node because it has a degree 2, and it is connected to two other nodes which have degree 1. And similarly 1212 are these terminal nodes, so they have degree 1, and they are connected to only a single node which has a degree 2. So by that simple numeric representation, we could figure out the unique topologies, and we found out that obviously trivially the standalone salt bridges, they have a higher chance to form, and they are the most overwhelming in terms of majority. But then we also found a lot of bifurcated salt bridges. We also found some cycles or closed chains, but they always sampled even number. You cannot have a odd number in these networks because of charge constraint. So you have a minus, then a plus, then a minus, then a plus, and you cannot have a fifth node here because it is forbidden because of electrostatic repulsion. So then we mapped the different kinds of motifs into the actual original structure, and found out that the bifurcated salt bridges, one of the major roles were to act as a molecular clip at a protein-protein interface. So that's where the bifurcation really comes into play, and these salt bridges, these motifs, they can be found close at the interface, closely spursed, and they can also sparse across an interface, and there are certain other functions that we actually mapped like this in the structures. Another set of motifs, as these complicated motifs, as you can see, really composite. So this is called 5 star because it has a star-like topology. It's made of 5 nodes with one central node, and this is a 4 cycle because it's a cycle, just consisting of 4 nodes. So here our hypothesis was that we can try to design for the future composite salt bridge motifs rather than standalone salt bridges, and that might have a chance to increase the probability of a design rescue. I'm not saying that you would get returned the exact design that was aimed for, but at least they, since these are present in at least in globular proteins in certain secondary structural contexts, and also since we are increasing the local local charges, a certain region of the three-dimensional structure, local charge density, so that probably will be will provide a restricted or limited or constrained environment for these salt bridges to actually form in the context of the folding of the designed protein. But obviously this is a matter of experimental validation, one has to test, but this seems quite analogous to the idea of alternative packings of hydrophobic cores within proteins, where we have recently shown that the same hydrophobic core can be composed of alternative topologies, so certain global constraints needs to match. So this is worth trying, because nature actually harbors such motifs. Probably it will open up an avenue of research. So then carrying on our first work on salt bridges, we further explored salt bridges in intrinsically disordered proteins and explicitly in IDPs. The key question that we try to address here, that IDPs are characteristic of physical flexibility or structural plasticity, and they are also characteristic of accommodating a large abundance of oppositely charged residues. So the charged residues will always trigger the formation of salt bridges, because especially given the fact that the IDPs do not have a global minima structure, they are always hovering around local minima. So obviously there will be instances when two oppositely charged residues will come close, and probably there will be a formation of an ionic bond, and that will in turn impart local rigidity in the structure. So it seems paradoxical to the context of retaining physical flexibility. So how this seemingly contradictory phenomenon happen together? What is the meticulous mechanism, or is there a trade-off? That was our question. So we took 4 IDPs. 2 of them was completely disordered, and 2 of them were partially disordered, and we just carried out an explicit all water MD simulation, and then looked at different salt bridges. We started our exploration of the motifs and counted their numbers, and as expected it followed a similar trend to that of the globular proteins. These are instances where even within IDPs you can see the formation of composite salt bridge motifs. But then more importantly, when we looked at the persistence of these salt bridges across the structures, we found that the persistence have a very long range. I mean, they sample, the salt bridges actually sample highly persistent salt bridges, as well as moderately persistent salt bridges, and as well as low persistent salt bridges, followed by an exponential tail of fleeting salt bridges or ephemeral salt bridges, and they are transient in nature. So usually such a tail is they may seem unimportant, and people do not pay much focus on that. But in this case, in our study, this is where we found where the mystery lies. When we picked up this tail and the salt bridges we mapped, and we actually looked at the individual charged residues independently. So what is actually happening in context of these ephemeral salt bridges is that they are constantly changing partners. So that means, for example, in this case, this is beta amyloid, the causative protein of Alzheimer's. You have a 28 lysine here, and here you have superposed four conformations taken from different ends of the different epochs of the MD simulation trajectory. The 28 lysine, the same positively charged residue, this is in salt bridge with 4 different partners at 4 instances. So it is constantly or continuously changing their partners, and imagine this happening throughout the structure. It is not alone this particular salt bridge, but also other residues. It's like a ball dance that is happening probably, and people are changing partners all the time. It's that kind of a dynamics. So the salt bridges, in one sense, these ones, the transient ones, they're constantly forming and collapsing, and then throughout the structure this is happening. So it will always sample different conformations. So instead of imparting local rigidity, this is actually helpful for the IDPs to retain their characteristic physical flexibility. Then the reviewer asked a very interesting question, that how can you say that these are functionally optimized, evolutionarily speaking? So is there a selection of such a distribution of salt bridges? So to address that, we took this very well documented interaction in terms of all the biophysical assays, interaction between tubulin and alpha-synuclein, which is the causative protein of Parkinson. And people have done pull down assays, and they have literally done all kinds of biophysical assays to characterize where exactly tubulin binds, and so we started on that as a docking site, and this is the middle domain. Interestingly enough, this region itself does not harbor any charge residues. The charge residues are on the terminal domains, and the tubulin, the alpha-synuclein, it in its dynamic trajectory, it starts with an open conformation and then gradually tries to close, and that preference is significantly enhanced if you put in the system the tubulin correctly docked at the docking site. So basically it wraps around the tubulin structure, that is the closed conformation, and obviously then this is stabilized, or at least a significant part of the interaction is stabilized by formation of interchain salt bridges. So that is a tubulin side chain, charge side chain, that is exchanging partners, or that is involving in salt bridge formation with alpha-synuclein oppositely charged partner. And when we looked at when we tried to map these interchain forming salt bridges in the original alpha-synuclein structure, this was very interesting to find out that these salt bridges are the ones which are transient, not the ones which are persistent. So that probably makes sense, because they are constantly forming and collapsing and playing this kind of a breathing kind of a motion within the IDP structure, and which makes them amenable and accessible to formation and interchange of their ionic bonds. And whenever there is a proper binding partner, they welcome it. I mean, they have the potential to do so. On the other hand, the high persistent salt bridges usually are made of short range contacts, so basically 2, 3, 4, 5, 10 residues long. So the interaction therefore is quite stable. It is not so easy to dislodge such an interaction by an exchange method, which is also probably one of the causal factors. So this is one of the hypotheses that we could put forward, that as a functional optimization. We performed certain mutational studies as well. I'm not going into that because of time constraint. The next thing that we explored, and this I did with my friend from mathematics, Abhirup. He is currently in Amsterdam doing postdoc. So here our question was that, okay, IDPs, they are disordered, but is there I mean, we can phrase the question like this, that is there an order of disorder, or is the disorder entirely random? Because we know that rugged energy surfaces are characteristic of IDPs. They do not have a global minima, but they hover around multiple local minima in the rugged energy landscape. So, regarding the physical flexibility and different conformations sampled, is there a conformational preference in other terms? That we tried to address. We took a statistical mechanical approach and studied the problem using phase transition, simulated phase transition dynamics, and of course we explored solid bridges and tried to find out a mapping, a possible mapping. So the mathematics part which Abhirup did for this, we essentially computed the probability of attaining a particular conformation at a given time, steady state probabilities that is, and the probability of transition between two states. And so he basically wrote these differential equations, and then we did eigenvalue decomposition to compute these matrices, and then followed by certain analysis which I am going to discuss on. But essentially the sum and substance of this work was that it revealed a critical nature of these of the conformational dynamics of our IDPs, and which resembled the avalanche dynamics characteristic of sand pile model. So in a bit more in a bit more structural terms, the IDPs, when we looked at the conformations, we found that conformations are centered around certain conformational cluster or cluster centers. The conformations are centered are clustered around certain preferred conformations, and those preferred conformations they deviate within a certain limit to a central conformation. So this we figured out by RMSD. We put a multiple cutoffs on RMSDs, and we did a clustering and figured out the clusters, different structured clusters, and then we took the central conformation from each cluster as a representative one. And this is the same for partially as well as completely disordered proteins. And then we started the simulated phase transition dynamics. So effectively we were looking at the dynamics or the probability of attaining and retaining one or multiple conformational states along time. So as you can see, certain conformations will be less preferred with time, and certain other conformations will be more preferred, but never there is a case of a single conformation that is predominating. Otherwise it will be probably the signature of globular protein if you perform a similar kind of analysis here. So obviously they are dispersed around multiple conformational states, but those are not really entirely random, first of all. And the second thing is that they are not pointing to a single conformation by any means. So there are always dispersed around multiple conformations, but with time certain conformations take hold. I mean, you can say it like that probably. So then we mapped the salt bridges on each of these conformations, and we found out there are two categories of salt bridges, if I may put in that way. There are certain common salt bridges common to all conformations for a given IDP, and again there are certain salt bridges which are unique to a given conformation or a given conformational cluster. So obviously the unique salt bridges interchange, I mean they undergo the transition, they can act probably like switches in these phase transition dynamics. And again the common salt bridges, most of them they were persistent and they were short ranged, so that's why they are there always, while the others change, interchange in that way. And then we performed a frequency distribution analysis of persistence of these IDPs along their state transition dynamics, and we found out that if you do a log-log plot, it follows a power law with an exponent which is greater than the magnitude of the exponent, that is the gamma, which is greater than 1 in most cases, bearing beta amyloid where it is just trending to 1, and so that makes these these points fit to linearity with a descending slope, and this effectively means that there are signatures of scale invariant self-similar fractal geometries. So that means although if you consider, let's say, 6 conformational clusters or 6 different preferred conformations for a given IDP in its trajectory, so these 6 different conformations, they are different, but they are also self-similar. So that means there are certain common features that are preserved. For example, the common salt bridges that we just talked about, they are always present there, and this is this makes sense, because then they can the dynamics can actually lead to the critical behavior following a structural degeneracy. So wherever you have a criticality, you have to exceed a certain barrier in terms of energy or in terms of certain other phase transition dynamic parameters, and this is analogous to the sand pile model in a sense that to be able to predict the exact critical point is difficult. It is sort of unpredictable because of the stochastic nature. So in a sand pile model, what happens, you have a pile of sand and you pick up a few grains and just drop on that pile. In most of the times they will be absorbed or buffered, but again at a certain very difficult to predict instance, you will see there is a landslide kind of event, so the entire pile will collapse. So that is the critical limit, critical threshold, and this is difficult to predict, and it has a stochasticity inbuilt. So there appears to be an order among the disordered states of an IDP as well. They are not exactly entirely random. That was our understanding of the topic, and the salt bridges holds the key for transitions between one disordered steady state to another disordered steady state. So that was another interesting observation. Till this point, we had done some three works on this, and we had a nice collaborative group obviously, starting from Professor Parvati Vishwas, who is in Delhi University, Department of Chemistry, where I spent as a postdoc 1 year, and then followed it up with other follow-up chapters on the same subject. Now then the COVID pandemic came, and in the first year of the pandemic, the focus of the research community or COVID research community was primarily on the interaction between the receptor binding domain of spike protein and its cognate receptor in the human lung cell, which is the angiotensin receptor. So that's basically a physics window, because you are dealing with van der Waals interaction and other non-covalent interaction, the collision, the laws of collision, etc. In the next year, we saw there is a noticeable and unmistakable shift in highlight. So from that physics window, the focus came to a chemistry window where we were talking about the furin cleavage of the spike protein at its S1 S2 junction. So this is a wonderful commentary published by Professor P. Balram, which was probably the first statement on behalf of an argument that is still going on the COVID origin. Before that, it was at least I didn't find any paper focusing on the alternative origin theories of COVID. Even in some of the advertisements, some of the posters, I have seen that these articles were censored. But interestingly enough, pangenomic and epidemiological studies revealed the entire sequence of all the coronavirus lineage viruses, and there was then a genome mapping done, and people found out that there is a motif called PRRAR, which is a polybasic arginine rich furin like cleavage site motif, which is which drew much attention of the community because of its seemingly sudden emergence in the SARS-CoV-2 genome, and that is exactly present at this S1 S2 junction. Now let me mention categorically that this is a step which is a non-essential step for the viral invasion, but if this step is executed, then the viral transmissibility is enhanced enormously, because the RBD, the receptor binding domain, is getting dislodged from the rest of the spike structure, and obviously this helps the kinetics of the transmission dynamics of the protein. It helps the viral fusion, and the viral life cycle is propagated. So probably this is one of the key reasons for which SARS-CoV-2 has this jumped increase in transmissibility with respect to the earlier onsets of the similar viruses, for example the one that caused the epidemic in 2003. And when we looked at these alignments in terms of proteins and also in terms of their corresponding genomic sequences, we found that there were certain signatures which at least shed some doubt on the natural origin hypothesis. I would request whoever has not read this commentary till now, please go ahead. And I'm not really going into the genomic details, the codons that has been used, all these details are there. But my focus for this particular work was that I was kind of blown away by the presence of these three arginines in such a close gathering, which will obviously impart a lot of disorder, a lot of steric and as well as charge repulsion. So then I looked at this problem from a structural dynamics point of view. In that hunt, we performed a series of docking studies, not only a single docking, we did ensemble docking, we did blind docking in class pro, we did guided docking using the FLCS as the dockable active site for the furin in ZDock, and it was really thorough, that I can tell you. And after that, after doing all the cross validations, we found out certain conformations, again not a single conformation I'm talking about, and took those top ranked docked structures for explicit MD simulation for long run. And then we since there were a lot of arginines, my intuition was that is there again a case of salt bridge formation. Salt bridge is here too. So for that we first looked at the furin structure, and we found out that the dockable site has a groove. The dockable site for FLCS, that is the little loop here in yellow, it has a groove, and where the catalytic triad of this protein, which is a serine histidine aspartate catalytic triad, that is very close to that groove. So if this can be entrapped in this groove, it will probably facilitate the cleavage enormously. And around this groove there are a preponderance of probably strategically positioned negatively charged residues. So obviously the chances of formation of salt bridges was enormous. So then we actually figured out all these salt bridges and performed the same analysis again, and we found out that there were very highly persistent salt bridges. Almost 90% of the time they are present. So it is indeed holding it tight so that the X can be so that the chopping can be performed. And then the other interesting thing I found out that I at least surveyed some 70-80 spike structures from the PDB, and these structures are mostly electron microscopic structures, and they are solved with abrogation as well as certain mutations, stabilizing mutations, so that image pattern can actually be generated, so that the protein becomes stabilized. In not a single of these structures could I find the coordinates of the FLCS loop. So it was entirely missing, and that kind of labeled the authority that it is a disordered loop, and people have also mentioned in the structural studies that this is a disordered loop. So starting from there, the intuition made us think in this way that salt bridges are probably forming these very highly persistent salt bridges. They're holding the loop tightly, that is facilitating the cleavage, and this is undergoing therefore a disorder to order transition. So I'd show a little video. Yeah. So in this little 30-second video, I just joined a few pieces of clippings from the 500 nanosecond MD simulation trajectory of the top ranked docked pose of spike furin. As you can see, the salt bridges are always present. I have only shown the highly persistent salt bridges, and so as opposed to the transient nature of the salt bridges, which was instrumental for disorder to disorder transition, it appears that persistent salt bridges holds the key for such disorder to order transition. And it is very interesting that for the 3 arginines, there is always 3 negatively charged residues coming from furin, and these 3 charged residues they have a lot of backup. So if at one instance, at one frame, if a salt bridge is not forming with let's say residue 1, it is always forming with residue 2 or residue 3, because there are a lot of it's not a limited number of negatively charged residues around that. Of course, a limited number, it's not a low number of a limiting number. I mean, there are a lot of other residues that can actually fill up for the salt bridge formation, if I can put it that way. So we used the Ramachandran plot, and we used an adapted formalism of the Ramachandran plot. I am coming to that in the next slide. So here, first of all, this is this is quite clear that this is going through a disorder to order transition. However, as you can see, here also for the order transition also, for the disordered or unbound state also. So this is where we plot the phi psi angles of the PRR AR motif, in its disordered state compared to its ordered state, and we sampled at a certain interval from the MD simulation trajectory, corresponding MD simulation trajectory. So we ran in background এটা একটুখানি withdraw করছি, এটা ভুল বলতো. Okay, so but the fact that these points are actually falling in the regular secondary structural region doesn't really truly portray the nature of the structure, if not the connection, the order is taken into account. So to take into account that as well, what we did, we joined the adjacent phi psi points in the Ramachandran plot. Now we have an understanding, a better understanding probably, that although these are falling in the regularly secondary structure regions, or the allowed regions of the Ramachandran plot, there is never a stable structure here, because the first point is probably falling here, then the next point is probably falling at the extreme end, so it's probably, this is beta sheet, then again a right-handed helix, probably then the next point is left-handed helix. So it's a tug of war that is going on, while if you look at the bound state, they are closely clustered between helices and beta sheets. So again, we are not really emphasizing the fact that it is forming a helix or a beta sheet, but definitely a disorder to order transition is taking place, and that also harbors the signature of metastability. That will be clear in the next slide, but before that, let me just complete this story that we computed. We designed a metric in this vector space, 2D metric, that is basically the distance between the phi psi points in this 2D plane, and then we did some statistics like computing the decile or the quartile, 75th percentile, and then we did a test of significance, and we found out that these changes are really significant, just like chi-square. So in the last diagram, I will show the energy calculations that we performed using Foldex, which is kind of a state of the art from in structure based thermodynamics in these days, where we found out that the average delta G of interaction, delta G binding or interaction, whatever you say, that is mildly disfavored. It has a mean value of plus 3.5 kilocalorie per mole, but it has a standard deviation of equal magnitude. So obviously this is this is close to that 0 point where where you do not have a preference, but still it is mildly disfavored. So that is probably anticipated, because the aim here is not to deadlock the structure in a jammed conformation, otherwise the cleavage won't probably have not occurred. So probably this is also justifying the fact that we need, if we want to lay our X on something that is always wobbling, first of all we need to have a good grip on that object, and that grip may not be the disorder is such that it is very transient, very temporal. So very many times there would be the opportunity to just lay the X or catalyze the proteolytic cleavage, but it's not really a particular conformation. Probably that is also speaking for the metastability, and as there is a large amount of disorder to take care of, entropy arrest has to happen in case of such a disorder to order transition, and that is also reflected in this energy diagram, where you have the entropic terms and the enthalpic terms. They are falling opposite, they are having opposite trends. So that also speaks for an enthalpy entropy transition. So this is where I would like to summarize. So probably this probably will be cross validated with certain other studies, but at the moment it seems very difficult to have an experimental solution to this, because probably you have to design then a non-hydrolyzable analog of the spike protein, and in context of proteins probably that is not so easy to come up with. Then only you can, since the reaction is always happening at the speed of knots, so it's very difficult to entrap that conformation. If you do not have a non-hydrolyzable analog, it apparently is difficult, and one may follow it up with a quantum chemical analysis to focus more on the cleavage, the actual enzymatic reaction that takes place. But again, that is probably very lofty, because it's a large system. So this is where we stand in Frontiers in Molecular Bioscience research topic, where I am serving as a guest editor. So you are all welcome to submit your articles and browse through it. You will get it from my homepage. This is currently my network. So as an independent researcher affiliated to an UG college, I really find not so easy to keep on pursuing your interest, but I have the privilege of a lot of collaborators both from and outside the country. এবারে শুনি কার কি প্রশ্ন আছে। হ্যাঁ বলো।
Just a suggestion, not question. আমি যেখানে এখানে বাকি দুজন কোঅথার, আমি একমাত্র যে কোঅথার নই এবং এই ফিল্ডের সাথে যুক্ত নই আপাতত। So I had difficulty understanding your inferences in two cases. একটা হচ্ছে frequency versus persistence যে ম্যাপটা তুই দেখিয়েছিস, ঠিক আছে? This one is এখানে একদম ক্লিয়ার কাট ইনফারেন্স আমি কিন্তু পাইনি। মানে if you say on the last যে আমি মানে disorder মানে there is a salt breach which is more flexible that will lead to disorder, and if it is more persistent that will not lead to disorder. So this is very flat inference that you are drawing. So inference wise I think your paper has better inference in this, কিন্তু আমার কাছে সেই এটা আসলো না।
আমি একটা মিসও করে গেছি, সেই কথাটা একটু মিস করে গেছি সিম্পলি সেটা।
ইনফারেন্স আরো স্ট্রং, আই এম শিওর ইওর ইনফারেন্সেস আর মাচ মোর স্ট্রং, কিন্তু আমার কাছে মানে বিং আ আউটসাইডার টু দিস আমার কাছে এই জিনিসটাই এলো ইনফারেন্সটা
একদম ঠিকঠাক ধরেছো। হ্যাঁ আমি বলছি তোমাকে যেটা মিস করে গেছি সেটা হচ্ছে যে যখন এই গামার ভ্যালুটা 2 to 3 এর কাছাকাছি আসে সেইটা হচ্ছে ক্যারেক্টারিস্টিক ফর স্কেল ফ্রিনেস। এই কথাটাই আমি বলতে ভুলে গেছি, স্কেল ফ্রিনেস কথাটাই বলতে ভুলে গেছি। একটা পাওয়ার ল ডিস্ট্রিবিউশনের গামা বা এক্সপোনেন্ট সেটা যখন 2 to 3 এর কাছাকাছি আসে, যত আসবে তত স্কেল ফ্রিনেস বোঝায়। এবার স্কেল ফ্রিনেস হচ্ছে কীরকম একটা জিনিস, যে ধরা যাক তুমি একটা এই ধরনেরই একটা স্ট্রেট লাইন তুমি ভাবো, যার অ্যাক্সিসের যে মানে টিক্সগুলো মানে অ্যাক্সিস লেভেলসগুলো এগুলো যদি তুমি ইরেজ করে দাও, করে একটা সম্পর্ক ধরো এটাকে 10 দিয়ে গুণ করলে, এটাকে 10 দিয়ে গুণ করলে, বা এটাকে 1000 দিয়ে গুণ করলে, এটাকে 1000 দিয়ে গুণ করলে, হ্যাঁ, এই সমস্ত প্লটসগুলো, এই সমস্ত মানে ডিফারেন্ট প্লটস, মানে একটা ধরো 1 to 10 ভার্সেস 1 to 10 প্লট করা, একটা 1 to 1000 ভার্সেস 1 to 1000 প্লট করা, একটা 1 to 1 প্লট করা, like that, they will superpose on top of each other if you use the same dimensions, actual physical dimensions for your plot. So that is the signature of scale freeness. এখন scale freeness এর সঙ্গে exactly এই self similar fractal geometries এর যে সম্বন্ধ, সেইটা আমিও যে খুব ভালো বুঝে গেছি তা না। যেটা আমি আমার মতো করে বুঝেছি সেটা হচ্ছে যে এই যে কনফার্মেশনসগুলো, এই যে ধরো এই যে কনফার্মেশনসগুলো, এদের মধ্যে একটা সেলফ সিমিলারিটি আছে, মানে এরা আলাদা কিন্তু এরা আবার একই রকম। এরা মানে স্ট্রিক্টলি স্পিকিং এরা আলাদা মানে হয়তো এখানে দেখো দুটো হেলিক্স কাছাকাছি এসছে, এখানে এই দুটো হেলিক্স দূরে দূরে গেছে, কিন্তু এই যেটা আমি তোমাকে এর আগেও যেটা বলছিলাম অল্টারনেটিভ কোর্স অফ হাইড্রোফোবিক প্যাকিং, হ্যাঁ, যেটা আর কি গার্গির যে পেপারটা, হ্যাঁ, সেখানে ওরা কি দেখিয়েছে, সেখানে দেখিয়েছে যে একটা প্রোটিন কোর, হাইড্রোফোবিক কোর, তার নির্দিষ্ট টপোলজি বেসিসে যদি আমি কোরকে ডিফাইন করব কি করে, একটা ডেফিনেশন হচ্ছে তার নেটওয়ার্কটা কেমন ফর্ম করছে, মানে টপোলজিটা কেমন, সেই এক্স্যাক্ট টপোলজিটা যদি নাও থাকে তাহলেও কোরটা থাকছে। কোর মানে কোর বলতে আমি বলছি যে ধরো একটা বিটা ব্যারেল, এবার একটা বিটা ব্যারেল, হ্যাঁ, মানে তুমি এটা বলতে পারবে না যে ফোল্ডটা চেঞ্জ করে যাচ্ছে, ফোল্ডটা একই থাকছে কিন্তু বিভিন্ন মানে যত মত তত পথ আর কি, অনেকগুলো ওয়েতে সেটাকে তুমি, তার মানে দেয়ার আর সাম গ্লোবাল কনস্ট্যান্টস দ্যাট নিডস টু বি স্যাটিসফাইড। হ্যাঁ, এবারে এই প্রবলেমটার ক্ষেত্রে এক্স্যাক্টলি সেই গ্লোবাল কনস্ট্যান্টসগুলো কি, উই হ্যাভ নট রিয়েলি গন ইনটু দ্যাট ডিটেল, বাট দ্য স্কেল ফ্রিনেস ইজ ওয়ান অফ দ্য সিগনেচার অফ scale and invariant fractal geometries. This much I understood. আর আরো একটা কথা বলি, এর পরেও আমি,
I mean, if you zoom at, say you have scales in thousand and millions, if you zoom on that scale, and if it's really scale free, then for every scale the figure will look similar. And this similarity is fractal similarity. If you zoom a fractal figure, for example, if you zoom, you will see again the same figure. Again, you zoom, say 100 times, you get the same figure. So this similarity basically is propagated or eventually is somehow mathematically computed as the scale freeness. আমি একটা কথা বলতে চাই, however, that say there are several intrinsically disordered proteins. We can somehow clusterize them in several groups. Now these groups are self-similar, means first of all an IDP doesn't have any globally minimal structure in terms of energy. Now these individual clusters, they also doesn't have any such globally minimal structure. Otherwise, you should get a globally minimal structure. So these clusters, again, you can clusterize a particular group into several clusters like that. And that's where the self-similarity lies. And again, the dynamics is such that it could it could have a phase transition from one group to another group. And that's how this structural degeneracy in IDP.
হ্যাঁ হ্যাঁ হ্যাঁ, মানে দ্য
আমার
স্ট্রাকচারাল,
মনে হয়
আমি একটু বলে দিই, সঞ্চিতা দির প্রশ্নের উত্তরটা দিই, তারপর শুনছি।
হ্যাঁ,
আমি বলছি যে স্ট্রাকচারাল ডিজেনারেসি ইজ ওয়ান অফ দ্য কি ফর ট্রিগারিং দ্য ক্রিটিক্যাল বিহেভিয়ার। মানে স্ট্রাকচারাল ডিজেনারেসি না থাকলে কিন্তু ক্রিটিক্যালিটিটা পাওয়া যাবে না। হ্যাঁ, মানে এবং এই সেলফ সিমিলারিটি দুটো ফ্যাক্টর, একটা হচ্ছে স্ট্রাকচারাল ডিজেনারেসি, মানে যেমন কোডন আর জিনিনের 6টা কোডন, তাহলে স্ট্রাকচারাল ডিজেনারেসি আছে। মানে যেখানে আর কি তোমার তুমি যদি ওই গেট লজিকে ভাবো, গেট লজিক তোমার আউটপুটটা মাল্টিপল ইনপুটস থেকে আসছে, একই আউটপুট, ঠিক আছে? তাহলে ডিজেনারেট স্টেটস আছে। আর কি না, তারা বেশ কিছু ফিচার যদি আমি দেখি, একটা পয়েন্ট আমি এখানে অবশ্যই বলতে চাইবো, যেটা এনার্জির কথা অভিরূপ আনলো। এরপরে আমি একটা অ্যানালিসিস করেছিলাম, অভিরূপও ছিল তার মধ্যে, সেটা ইনকমপ্লিট থেকে গেছে। আমরা খুব ইন্টারেস্টিং জিনিস পেয়েছি। সেটা ইন্টারেস্টিং এই অর্থে যে লোকাল মিনিমার কথা যখন আমি ভাবছি, এরম নয় কিন্তু যে একটা কনফার্মেশন একটা লোকাল মিনিমাকে ম্যাপ করছে। হ্যাঁ, মানে এনার্জি টার্মসে আমি যদি ভাবি, তাহলে কিন্তু দেয়ার ইজ নো ডাইরেক্ট কোরিলেশন বিটুইন দ্য কনফার্মেশনস অ্যান্ড দ্য এনার্জি। কেননা এনার্জি এমন একটা প্যারামিটার যেখানে একটা হাইড্রোজেন বন্ড তৈরি হওয়া বা বন্ধ হয়ে যাওয়া, সেটারও একটা সিগনিফিকেন্ট কন্ট্রিবিউশন আছে। হ্যাঁ, সো মানে একে যদি আমি কোনো এনার্জি ইকুইভ্যালেন্ট টার্মস বা কোনো স্কোরের সঙ্গে যদি ম্যাপ করতে চাই, তাহলে আরও সফিস্টিকেটেড মেজার ভাবতে হবে, এনার্জি দিয়ে হবে না। কি বলছি বুঝতে পারছো? এবারে আমি একটা অ্যানালজি দিই, তাহলে পুরো পরিষ্কার হয়ে যাবে। আইডিপি ইজ অল অ্যাবাউট অ্যানালজি। সেটা হচ্ছে যে ধরো একটা ভবঘুরে, আমরা যেরকম জীবন কাটিয়েছি, অভিরূপ সেরকম জীবন কাটিয়েছি, একটা ভবঘুরে তার নিজের বাড়িতে মন টেকে না, বা নিজের বাড়ি বাসযোগ্য নয়, বাড়িতে থাকতে পারে না, তাহলে সে কিভাবে দিন কাটাবে? সে এর বাড়ি তার বাড়িতে ঘুরেই দিন কত ঢের কাটে। এই হবে, সে আজকে তার বাড়ি, আজকে অমুকের বাড়ি, কখনো ফুটপাত, কখনো গাছতলা, কখনো এয়ারপোর্ট, এইভাবে কাটাবে। কিন্তু এই যে তার এই যে ভবঘুরে দশা, এই ভবঘুরে দশারও কিছু প্রেফার্ড জোনস থাকবে, যত্রতত্র সর্বত্র কিন্তু পারবে না। মানে এবার যদি সে একটু বাবুয়ানা ভবঘুরে হয়, সে গাছতলায় থাকতে পারবে না, বা সে পাকা পায়খানা না হলে হাঁটতে পারবে না, এমন ভবঘুরে যদি হয়, তাহলে তার কিছু এসেনশিয়ালি কিছু লোকাল মিনিমা থাকতে হবে, কিছু বন্ধু বান্ধব থাকতে হবে, যারা তার এই ভবঘুরে ব্যাপারটাকে সাপোর্ট করবে। ঠিক আছে, এইটা এবং তারপরে কি, এবার সেইটার যে বিচারটা চলছে, ধরো আমার 6টা বন্ধুর বাড়িতে আমি বছরের 6টা সময় থাকি, এই যে ঘুরে ফিরে আমি বলছি, তো কিছু একটা কমনালিটি হয়তো আছে, যে কমনালিটিটা আছে বলেই আমি সেই 6জনকে বাকিদের থেকে বেছে নিয়েছি, বা তারাও আমাকে বেছে নিয়েছে, সেইটা হয়তো এনার্জির সঙ্গে ইকুইভ্যালেন্ট। সেটা কিন্তু মানে এমন একটা এনার্জি বা এমন একটা বেস লেভেল। হ্যাঁ,
এই 6জন আবার 6জন বউ নয়, তাহলে ব্যাপারটা থাকে না। প্রত্যেকটা ক্লাস করে যদি একটা গ্লোবাল মিনিমাম,
তাহলে গ্লোবাল মিনিমাম না হয় গ্লোবাল ম্যাক্সিমাম হয়ে যাবে।
না, অভিরূপের এই অ্যানালজিটা এইবার আমার পরিষ্কার হয়ে গেছে, যে ফ্র্যাক্টালে ওই তুই পৃথ্বীও বুঝতে পারছিস, সেটা কিন্তু খুব সুন্দরও বললো, যে স্কেল ফ্রিনেসে আমি যেটা বললাম না, প্লটগুলো মার্চ করে যাবে, স্কেলটাকে যদি চেঞ্জ করি তাও, তো সেইটা ফ্র্যাক্টালকে রেফার করছে। কেন? তার কারণ হচ্ছে ফ্র্যাক্টালের বৈশিষ্ট্যই কি, যে একটা মোটিভ, সেটাকে এনলার্জ করো, আবার ওই মোটিভ আবার এনলার্জ করো, তাকেই তো ফ্র্যাক্টালের যে কত রকমের মানে ড্রয়িং আছে, তাই না?
আমার মনে হয় যে এইখানে মানে তুই ওই যে রামাচন্দ্রন প্লটের ছবিটা,
হ্যাঁ, ওইখানে একটু আমি আরো ভালো করে বলতে,
যদি করা যায় তাহলে ব্যাপারটা খুব ভালো বোঝা যায়। মানে there is really a tug of war between different structures, say dictatorship or
এখানে সঞ্চিতাদির জন্য আমি বা পৃথ্বীর জন্য আমি আর একটু বলি, সেটা হচ্ছে যে এখানে কি বলতে চাইছি না, রামাচন্দ্রন প্লটে তো ফাইসাইয়ের ডিসক্রিট পয়েন্ট হিসেবে প্লট করার ট্র্যাডিশনালি এইভাবেই ব্যবহার করা হয়। কিন্তু আমি এখানে এই প্লটটা দেখে আমার মনে হবে বাহ কি আনন্দ, এটা তো তাহলে সবকটাই তো অ্যালাউড রিজিয়নে পড়ছে। হ্যাঁ, কিন্তু
অ্যালাউড রিজিয়নের মধ্যে কন্টিনিউয়াসলি চেঞ্জ করছে, কিন্তু অ্যালাউড রিজিয়নগুলোর মধ্যেই থাকছে, মানে देयर इज আ টেন্ডেন্সি টু বি ইন দ্য অ্যালাউড রিজিয়ন, কিন্তু কন্টিনিউয়াসলি চেঞ্জ
হ্যাঁ,
করছে। দিস ইজ ভেরি
কিন্তু অ্যালাউড রিজিয়ন বুঝলাম, কিন্তু কি হচ্ছে ধরো এইখানে যদি একটা পয়েন্ট পড়ে, একটা পয়েন্ট, সিঙ্গেল পয়েন্ট, তার মানে একটা হেলিক্যাল টার্ন তুমি ভাবতে পারো, একটা হেলিক্যাল টার্ন, তার পরের পয়েন্টটাই গিয়ে পড়ছে ঠিক, মানে এটা লেফট হ্যান্ডেড, এটা রাইট হ্যান্ডেড হেলিক্স, তার মানে একটা টার্ন হলো লেফট হ্যান্ডেড, তার পরের টার্নটাই আর ওদিকে না গিয়ে আর একদিকে ঘুরে গেছে। হ্যাঁ, তো ফলত এই পুরো জিনিসটা মিলিয়ে কোনো রেগুলার সেকেন্ডারি স্ট্রাকচার দিতে পারবে না, সেইটাই আরো স্পষ্ট হয়েছে এই ছবিটায় এসে। এইটাই আর কি, এটাই বলার চেষ্টা করছি। হ্যাঁ, লুপের মধ্যেও তো দেখো না, লুপের মধ্যেও দেখবে হেলিক্সের প্রবণতা আছে, কিন্তু মানে এই যে মলিকুলার গ্রাফিক সফটওয়্যারগুলো ওই মানে হেলিক্স আঁকবে না লুপ হিসেবে দেখাবে, সেইটা ডিপেন্ড করছে ওই ফাইনার অ্যাডজাস্টমেন্ট অফ দ্য মানে ফাইসাই ভ্যালুস। মানে ধরো -48 -58 হচ্ছে লেফট হ্যান্ডেড হেলিক্সের রামাচন্দ্রন প্লটের আইডিয়াল ভ্যালুস। তো কোনোটা যদি -40 -50 হয়, তাহলে সেটাকে মোটা রিবন দিয়ে দেখানোর প্রবাবিলিটি অনেক বাড়বে, রাদার দ্যান যেটা আর কি ধরো -25 -30, কথার কথা বলছি। তো সেই জন্য দেখবে লুপের মধ্যেও কিন্তু মাঝে মধ্যে এরকম ছোট, সেটাও যেন একটা হেলিক্সই, কিন্তু সেটা ঠিক ওই অ্যাঙ্গেলের টার্মসে আলফা হেলিক্স অবধি হয়ে উঠতে পারে। বিটা শিটে তো অজস্র উদাহরণ আছে, বিটা শিট তো লুপ খুব ইজিলি হয়ে যেতে পারে, বিটা শিট খুব টেন্ডার, আর যেহেতু বেশি জায়গা লাগে ইন্টারচেন হাইড্রোজেন বন্ড, ইন্টার মডিউল হাইড্রোজেন বন্ড যদি বলি, সেই ইন্টার স্ট্র্যান্ড হাইড্রোজেন বন্ড, সেই জন্য বিটা শিট মানে তুমি যদি একটা সার্টেন কাট অফ দিয়ে পিডিবির সমস্ত প্রোটিনকে ফ্র্যাগমেন্ট করে নাও, তুমি দেখবে হেলিক্স অনেক বেশি আছে, বিটা শিট অনেক কম আছে। এই আর কি, মানে ছোট মোটিভগুলো বেশি হেলিক্স হতে চায়, কেন হেলিক্স অনেক বেশি ইন্ডিপেন্ডেন্ট, কারণ ওখানে ওরই মধ্যে। হ্যাঁ, এই আর যাই হোক, এই হচ্ছে। আর কি বলছিলে অভিরূপ, বল আর কি, কার কি পয়েন্ট আছে, আর কিছু বলছি কি? বাকিটা ঠিক মোটামুটি, মানে কোনো মেজর কি বলবো, ভুলভাল কিছু বলছি না তো, এটাই আগে ক্লিয়ার। তারপর হ্যাঁ, আমি ওই রামাচন্দ্রন প্লটের ওইখানটা গিয়ে একটু ধেরিয়েছি, ওইটা একটু মানে যেহেতু প্রথমবার বললাম সেই জন্য। ঠিক আছে, বাকিগুলো তো বলেছি। আর যাক গে, সঞ্চিতা দি তুমি তো আর এলে না।